First, we explain what is a quantum walk. Quantum walk is the most elementary model for an electron moving along a line. It was introduced by Richard Feynman. It is also an archetypal model for studying quantum algorithms. Quantum walks on general graphs were shown to be universal for quantum computation. That is, they can solve efficiently any problem that any other quantum computer can. So let us proceed to Feynman's elementary definition. It is going to be a kind of formalization of the interference experiment shown on the figure. So imagine a checker that moves along an infinite checkerboard. A checker can move either upwards right or upwards left to the neighboring diagonal square. In the figure, we see two possible examples of checker paths. The black rhombi depict turns, that is, the points where the checker changes its direction. In the figure to the left, we have one turn, and to the right, we have two turns. Denote by turns of S the number of turns in a path S. We now introduce the wave function at a given integer point xt. It is given by the following formula. Here, the coefficient in front of the sum is just some normalization coefficient. And the sum is over all possible checker paths from the origin to the given point xt, passing through the point 1, 1. So each path contributes the following number to the sum. This is minus I to the power to the number of turns in the path S. Finally, the probability to find an electron at the point xt is the absolute value square of the wave function. We have defined a quantum walk, and actually we do not need any knowledge of quantum mechanics to understand this definition. To make it absolutely clear, let us work out a simple example, and we switch to a workout area here, where we consider the case xt equal to 2, 4. That is exactly the point shown on the figure. So each of the paths shown in the figure contributes to the sum. The left path S contributes the following number, which simplifies to just this. The right path S prime has two turns now. That means that it contributes the following number with a minus sign in front. We have also a third path looking like this that has the same contribution. And by summation, we compute the wave function at this particular point, which is going to be this number. And we compute the probability to find the electron at this particular point. It is going to be 5/8. Hope now the definition is completely clear. And we are going to study this probability distribution for large time t. Here the plot illustrates t equal to 1000. If we start from x equal to 0 and to increase it, then we first observe some oscillations, then a sharp peak, and afterwards we get an exponential decay. This observation has been proved rigorously in a seminal work by Sunada and Tate. So in the figure to the left, we depict the regions where the asymptotics were known before. In the left yellow region, it is yellow, believe me, we have oscillations. In the right yellow region, we have exponential decay. In the brown region in between, we have a phase transition described by the area function. So one should note that the result was not a uniform asymptotic formula. And also, there remain some wide gaps in between. Now, our main contribution is filling those gaps and providing a uniform asymptotic formula for the wave function in the whole domain where x over t is bounded away from 1. This is the yellow region in the right figure. One should remark that x over t has the meaning of average velocity, and in our units, 1 corresponds to the speed of light. So we are bounded away from the speed of light. Why do we care about such asymptotic formula? One reason that this allows us to find a precise asymptotic formula for the maximum of the distribution. So now the theorem. We should not care too much about these rather involved expressions. Let me just explain and discuss the key features of this result. First of all, we introduce the velocity v equal to x divided by t, and as long as it is bounded away from 1 and minus 1, we get some asymptotic formulae for the real and imaginary parts of our wave functions in terms of the so-called area functions. Here, the main terms can be easily computed by known methods. So actually our contribution and the hardest part is to get uniform bounds for the error terms here. We see that the error term is additive for small v and multiplicative for large v. Here, the notation O sub delta means that the constant understood in the big O notation depends on delta, but does not depend on x and t. And in the first case, big O does not involve any parameters. This is a uniform estimate with a constant not depending on anything. This is a key point. So, some plot to illustrate the approximation quality. Here, small blue dots represent the true values of the wave functions, and the red curve is the approximation. And what is really interesting for us is to discuss the ideas of the proof of this result, because here we introduce a completely new idea. So we start from something well known. It is a Fourier representation for the wave function. Here the key ingredient is this function omega appearing in the exponent, which has the meaning of energy. We are going to extend this function omega and its derivative to the complex plane. And in the work area, I should write down the expression for this derivative. It is cosine divided by the square root of the following shape. This function has a lot of symmetries, so that its value at an arbitrary point can be easily expressed in terms of the values in the so-called fundamental domain, which is defined on the slide and shown in the figure to the left. We also exclude a cut, that is a vertical ray here, just to make this square root a single valued function in the complex domain. This way, we get so-called domain D, which is the natural domain of definition for our function omega prime. And the key observation is that this function omega prime is actually a one-to-one conformal mapping of the left domain to the lower half plane. We were able to prove a general result about such conformal mappings. For the first time, we get a general theorem which allows to compute an asymptotic formula for an oscillating integral involving a Rie function with a uniform error estimate varied in the whole domain. We emphasize that the main term can be computed by well-known methods, but the main difficulty is to get a uniform error bound. And in many known computations of this kind, getting this kind of bounds is related to numerous assumptions throughout the argument. Magically, in our theorem, all these assumptions are observed by just one condition, that omega prime is a one-to-one conformal mapping to the lower half plane. As a result, our general theorem is just one slide long. You just have not seen the computations in particular cases which are present in books and take 20 pages or more. So actually, the proof of this theorem is also shorter than the proofs for existing particular cases. Here, the complex analysis allows us to replace local singularity analysis with a global picture which can be obtained from the boundary behavior of conformal mappings. So this is the main idea. And this is the final point of our previous research on this subject listed here. In particular, in the first link, you can find a zero-knowledge introduction to the subject. Now I wish to thank you and wish you a wonderful rest of the day.